Now we're going to introduce something called the dot product that we find between two vectors of equal length. So let's say we have vector u, which has elements u1, u2, dot, 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 down to un, and vector v, which also has elements v1, v2, dot, 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 down to vn. So they both have n elements, okay. Then u dot v, okay, that's the dot product, u dot v is equal to u1 times v1 plus u2 times v2 plus dot 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 plus un times vn. Okay, so this is a single number. It's not going to be a vector, it's a number. So for example, if we have u is equal to 1, 2, 3, and v was equal to 2, 0, minus 1, right? Then u dot v is equal to 1 times 2 plus 2 times 0 plus 3 times minus 1, which simplifies to 2 plus 0 minus 3, which is equal to negative 1. That's the dot product of these two vectors. Okay? Now you may look at this and say, something about this looks kind of familiar. Well, let's think about what happened. When I talked about multiplying these two matrices, let's say I had A was equal to A11. We'll just use square matrices, but it doesn't matter. A11, A12, A21, A22. And then we'll say B is equal to B. Actually, we won't make this one square just to make it clear that we're not requiring that. B11, B12, B13, B21, B22, B23. What happens when we're finding A times B? Well, the top number is going to be A11 times B11 plus A12 times B21. What am I doing there? Well, basically, each of these numbers that we find in the product here is the dot product of one of the rows of A with one of the columns of B. So the dot product is not about these being column vectors or these being row vectors. It's about matching up corresponding terms, multiplying them together, and then producing the sum of those products. So if we think about, we could continue this, I'm not going to. So if we think of A as being composed of these rows, we'll call this row 1, which is a row vector, right? That's this right here. And the second row, and I like to put these little lines on here to make it more clear. I'm talking about a row. That's this row. And multiply it times B, which consists of these columns. So I'm going to say this is B1 and put lines here. B2, that's a vector. Lines here, B3. Then what is AB? Well, it's A1 dot B1 right here. A1 dot B1. These are vectors. And then row 1 times the second column, right? So that's A1 dot B2. And then A1 dot B3. And then we repeat for the second row of A, which we're calling A2. So A2 dot B1, A2 dot B2, A2 dot B3. So when we've been finding the product of two matrices, at least using the way I've shown you, okay, really you can think of it as finding a bunch of dot products. Okay? So let's look at some of the properties of dot products. Now before we do that though, let me point out, if U and V are both column vectors, right? So we have this is vector U, this vector V, right? We say, okay, if we think about what I just did, where I'm taking the first element of this, multiplied by this, second element times the second element of this, and so forth, I can think of that as matrix multiplication if I write this. The transpose of U times V. So this is now U transpose times V, which means now I have a 1 by n vector times an n by 1 vector, which gives me a 1 by 1 value, which is just a scalar. That's really all it is. All right. So now let's look at these products, or these properties, excuse me. So for these, we have scalar k. And then we have n by 1 vectors, u, v, and w. So the first one says u dot v is equal to v dot u. Why is that? Well, if I'm multiplying the first number of u times the first number of v, does it matter which order I do that on? u1 times v1 or v1 times u1? No, it's going to be the same. And as we continue down, they all have to add up to the same amount. Okay? B, if I were to scale a vector u by scalar k, and then find the dot product of that new vector with v, that's the same thing as scaling the dot product of u and v. So k times u produces a vector, right? That's going to be this. Ku will be k u1, k u2, dot, 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 k un. Now I take that vector and find the dot product with v. That's the equivalent of finding the dot product of u and v and then scaling by k. Third one is kind of like a distributive property. That says if I were to add u and v, that produces a new vector, and take the dot product of that new vector with vector w, then that's equivalent to the dot product of u with w added to the dot product of v with w. And then finally, u dot u is greater than or equal to 0 if these are real numbers. U dot u is greater than or equal to 0 and is only 0 if u is a 0 vector. Right? Because if the first element of u is positive, then a positive number times a positive number is another positive number. If it's negative, a negative number times a negative number is another positive number. So the only way you can get 0 by multiplying two numbers together would be for them to be 0 to begin with. If you're multiplying the same number, that is, you're squaring the same number. Okay? So those are the rules for dot products. While we're here, though, let's do one proof. Now, I know you hear proof and you're probably going, oh, I don't care about proofs. Don't show me any theory. But when I started preparing to teach linear algebra for the first time, obviously there was lots of things I need to fill in. I know you like to believe anybody who teaches a class already knows everything there is to know. But the reality is, most of what I know about any class I taught, I learned while teaching the class. It's what really forces you to get in and fill in all the holes that you were happy to have as the student. But there were times I would read something in a book and think, wow, can that really be true? And then I'd sit down and work out some little proof and realize that, oh, yeah, that is really true. And I was able to convince myself. So let's go back to something we saw for transposes. I told you when we were talking about transposes that if A is an M by N matrix and B is N by P matrix, right? That means that I can produce AB, because these are the same, N columns here, N rows here. I told you if you take the transpose of that, that's equivalent to B transpose times A transpose. Now, is that really true? Now, the mistake to make on this is to look at it and say, well, since the shape of this has to be equal to the shape of this, then I know they're true. But that's not correct. The shapes obviously have to be the same. But as we saw with commutativity, if A and B are both N by N matrices, then AB is N by N, and BA is also N by N, but AB doesn't have to be equal to BA. So that's not the proof. But now that we know dot products, let's actually produce these. Now, I will tell you my proof skills probably offend real mathematicians because they're not very formal, but I think they're sufficient to convince you of the correctness of this. So what is AB? Well, if we think now we know dot products, this makes it a lot easier. So I can think of AB as being this. Row A1, row A2, dot, 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 down to row AM, right? And then B has P columns, so column B1, B2, dot, 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 BP. And if you want, you can draw the lines on here. So the first element here will be A1.B1, then A1.B2, dot, 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 A1.BP. And the second row will be A2.B1, A2.B2, dot, 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 A2.BP. And continue down, AM.B1. Work over to here, we get AM, right? The last row of this, last column of this, so it's BP. So then AB transpose, right? Now we'll have A1.B1 here still, but now A1.B2 on this first row here has to come down to this column because we're transposing this. So this now will be A1.B2. Continue down to A1.BP. Continue over this way. I'm with AM.B1. Work my way down. And AM.BP. And that's this. Okay? So what about the right-hand side? Well, B transpose A transpose means now I have row B1, row B2, dot, 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 row BP. And over here I have column A1, column A2, dot, 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 column AM. Or you could think of these as actually each being transposed. That's probably better. All right? So what is that? Well, B1.A1, the transpose here doesn't matter. All it's doing is taking it and turning it this way. But that's now making this B1, right? This is now B1 transpose. This is A1 transpose. So it just allows the product. But ultimately, I'm still finding the dot product of this with this, which is B1.A1. And then B1 with A2. Sorry, B1.A2. Dot, 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 B1 with AM. Well, what was this? A1.B1. Well, remember we said that A1.B1 is equal to B1.A1, so those are equal. AM.B1, B1.AM, that's equal. Continue my way down. I'm going to get BP.A1. A1.BP, those are the same. BP.AM. And those are vectors. AM.BP. So we could work out and fill in more of these dots, right? That's just my way of generalizing. But hopefully you can see why these two have to be the same. So this really is true, assuming you have the dimensions to allow the product in the first place. But lots of the proofs I do are really like this, just sort of algebraic type things. And you can do the same thing too. You just have to be willing to try. But that's the dot product.